as well. And some of the things are pretty simple. We'll start with something very simple. And though it appears very simple, last year examination, quite a few questions have come on this. See, typically when you look at any device you open, you'll find so many small like integrated circuits, so many small connections are there, so many small elements which consist in a circuit. So even the resistors also is actually very small in size, and they all look similar, but they have different value of resistance. So if you write the value of resistance, is difficult to read. Given the small size and given the problem that it may become difficult to read later on, rather than writing the value of resistance, they use something called color code. So we'll understand what does color code mean. The color code, this is kind of a small figure. You see on the right corner bottom, the figure what you see is example of color code. So if you have a cylindrical shape resistance, it has few bands. We see 4 color bands here. Okay, and these 4 color bands indicate what the value of resistance is and something more. That's why I'll try to understand what it is. So the number, so first there's some table like this. Different colors have a different meaning in terms of numbers and multipliers. So what does black color band indicate? 0 number or multiplier of 1. Brown color indicate number is 1, multiplier is 10 to the power 1. So you notice this, these two are related. In case of number, if it is 2, if it is multiplier, it is 10 to the power 2. So this is each color stand for a particular number from 0 to 9. And it has, in terms of multiplier, also it stands from 10 to the power 0 to 10 to the power 9. And then last 3 are little different. Last 3 we have gold color, silver color, and no color. This indicates what is the tolerance, how accurate the resistance is. If it is gold standard, the tolerance is within plus minus 5%. It means if it is 100 ohm resistance, its value is not more than 105 and not less than 95. If it is silver, tolerance is plus minus 10%, and no color means the tolerance is plus minus 20%. So this indicates 3 things. It indicates number, it indicates multiplier, it also indicates tolerance.
At
and
what
how do
temperature,
we
sir?
huh?
Temperature?
Temperature, no, but this is not temperature based, but this will be, most cases we assume the resistances
No,
are
the
made,
resistance are
made, see, if you, yesterday also talked about, there's certain resistances, certain material, like a magnenin, they have very little variation in resistance with temperature. So we assume most of the resistances what we use in commercially, those resistances for given range of temperature, the variations are very small within the tolerance. So it has nothing to do with temperature. Regardless of what the working temperature is, which is not going to vary too much, we assume the resistance to be within the tolerance which is given as per the color. So when you look at this, so this is something memorizing this. Memorizing this is whenever you need to memorize something like this, you'll have some easier way to memorize. So this also has easier way to memorize. So that's what we'll understand. What is the way to memorize all those colors? I think mnemonic what people commonly follow is order is what? If I know the order, black, brown, red, orange, yellow, green, I can place number 0, 1, 2. So all I need to know the order, and against the order, I can fill in the number. So what is order is, we pick up the first alphabet. What is the first alphabet? And this is a mnemonic we have. What is mnemonic? We'll see, write that one and then we'll understand. B.B. Roy of Great Britain had a very great wife. Okay. So what does this sentence mean? What are the terms highlighted word letters in bold? The first letter B, second alphabet B, third alphabet R, fourth alphabet O, fifth alphabet Y. So what is first alphabet? It starts from darkest color, which is brown. Sorry, black, and then brown. Third one is red, then orange, then yellow. G stands for green of Great Britain. B is for blue. Had has no significance. V is for violet. G for great. G for gray, and W for white, gray and white. So if I remember this one, if I write these numbers like this, any color I read, I can suppose I see, okay, violet color. Very easily you can read violet color stand for a number of 7, or for multiplier stand for 10 to the power 7. So I hope all of you understood how this mnemonic can be used to identify the number corresponding to a particular color. Okay. Shravani, have you understood this color code?
Yes, sir.
Some of you wondering why BB Roy of Great Britain? Why not BB Roy of India? It sounds like Indian, but it's okay. Perhaps that doesn't match the color code. So some people may have some doubt. I think we have to live with those doubts. Nothing we can do. Because this one makes it is easy to remember those codes. I hope all of you understand when you write, and below that if you write the numbers with each color, we can easily identify. And last year mains practically every paper had one question where resistance was given in terms of color code. So unless you know the color code, you can't find the resistance and you cannot proceed with the rest of the question. And these are the color code for the numbers ranging from 0 to 9, 10 values, 10 alphabets, 10 colors. And there are other two also, gold and silver. Gold is stand for tolerance of 5% and also for division by 10. So two things, gold is 5% and multiplier, it is -1, and silver is multiplier is -2 and tolerance is 10%. So rather than writing the number to indicate the resistance and its accuracy or tolerance, we use this color code or colored bands. Okay, and we start reading and we'll take one or two examples to understand how to apply. And this is pretty simple, no concept involved. It is more like biology, geology kind of thing, just remember. So we'll come to that one. So okay, maybe next slide we'll look at that part. So again, to recap, what are things we're going to use? We are going to use this number, and let's see one example, what the bands are. Okay, we start reading band from the right-hand corner. So when we see from the right-hand side, the first band, what does first band indicate? First band indicate will be either no band here, or it will be silver or gold. So rightmost band indicates tolerance. The last band indicates tolerance. If that last band both it is neither silver color nor gold color, it indicates absence of tolerance band, which indicates tolerance to be 20%. So this is something, and then we look at this other two. Now first two band indicates number, and the last but one indicates multiplier. Last one what indicates multiplier. So last one, see, so basically if I look at this, the one is last from rightmost. If it is gold or silver color, it indicates tolerance. Okay, then next to it indicates multiplier. But if the tolerance band is not there, the last band indicates multiplier. I hope that point is clear. Okay. So let's see if this is the given like this. What does it mean? I start reading from the top. First thing I notice, this color is silver. So I put this number is equal to 10%. Plus minus 10% is tolerance. Then I look at next to it is a multiplier, red color. Red color, I find what is the number corresponding to red is 2. So multiplier means in place of that this band, I put a number equal to 10 to power 2. Then I am left with two bands, both are red and red, which makes life easy. Both are red and red, I write the number as 22. So these first two indicates the numbers. This one indicates multiplier, and the last one indicates the tolerance. So we'll do one more, so that I think that's enough for practice. The last one, what you notice here is rightmost one is gold. So there is a band for tolerance. So band for tolerance, what I would write for gold? Gold color. Khyati, what do we write for gold color?
So 5%.
5%. This gold standard. The first thing we might notice this one, this is 5%. The brown indicates for what? Is it for number or multiplier?
Multiplier.
The brown is for multiplier. So I read the what is black, brown. Brown is 1. So multiplier is 10 to power 1, which is 10. Then I look at this last two. What is left is yellow and violet. Yellow and violet indicates number. Let me read. Yellow is 4. And where's violet here? Violet is very great wife. No, this is something really funny. Very great wife. It sounds untrue, but it is, you can take it, okay. So this is 7 number. So 4, 7 number, multiplier, tolerance. So there's no, just follow the method, just follow the rule. We can, any color codes are given, either in the exam paper, if they don't print in color, they may write these colors, which makes easy. So those who have a problem identifying the color also will not have issue in the examination paper. So so I hope all of you understood why do we use a color code. because given the small size of resistor, it's difficult to read the value. Hence, we use the color code. It may have 4 bands. And we'll see later, I think those IP book, they have given 4 bands, and NCERT book, which is standard book. But sometimes in the exam, they have also given 5 bands. If there are 5 bands, first 3 will indicate number, last one indicate the tolerance, last but one will indicate the multiplier. So if there's one more band here, so will be 3 numbers here, kind of thing. But for now, let's limit to this. We'll see some of those later. So this is easy part. If any such question come, it's really easy to find out value. Okay, now we come to some part of Kirchhoff law, which we briefly discussed in previous chapter. We did discuss about Kirchhoff loop rule. There's a Kirchhoff junction law also. Kirchhoff junction law is extremely simple law, and something you will wonder why there should be even a law. This is something intuitively you understand, and it is junction law, so it's applicable to a junction in a circuit. Sum of current entering the junction in a circuit is equal to sum of current leaving the junction. It is also, we can also say, this particular law is more like conservation of charge. Junction doesn't carry any charge. It means whatever charge comes in a given time, the same charge has to go out. So if we take the time interval to be 1 second, whatever charge coming in 1 second is equal to current coming in, and charge going on per second is equal to current going out. So very simple law. So sum of current entering a junction. So suppose a junction is given like this. This is part of the circuit. Here we find I1 and I2 are currents entering. So current entering can be written as I1 plus I2. And current leaving is I1 plus I3 plus I4. These are the 2 currents which are going out of the junction. So this law simply says I1 plus I2 is equal to I3 plus I4, which is so intuitively, I think without the law also we could have done it. But Kirchhoff wanted to have his name somewhere. So he made this law and his name lives forever, kind of thing. Other way of alternatively, we can state the law in other form. Other form, we can say the algebraic sum of current directed towards junction is 0. What does it mean? We have indirectly applied this to a Y kind of question in case of capacitor for charges. So let's see what does it mean. So when we say directed towards junction, algebraic sum means it can have positive value, it can have negative value. So we have to define what is positive, what is negative. Current directed towards junction is taken as positive, and current directed away from junction is taken negative. If we write in that fashion, the net sum equal to 0. So this junction, if we have to apply the second way of writing Kirchhoff junction rule, this I1 is directed towards junction is taken positive. I4 is directed away from junction is taken as negative. I3 also away from junction negative. I2 is directed towards junction is positive. So if I write sum of all 4, I write I1 plus I2 minus I3 minus I4 is equal to 0. So that's alternate way we can write. That's a Kirchhoff junction law or junction rule, which is extremely simple. Again, we go to Kirchhoff loop rule. Yes, Vignesh, you have some question?
Sir, that law was assuming that it's always in steady state, right, sir?
Even if it is not a steady state, it is based on the fact, can a junction hold any net charge? But junction is a point. It is not even a steady state, even otherwise also, the junction cannot have any charge. So it's like this, water is flowing through 4 pipeline. What is in the junction, what will happen even if the flow is not steady? Even for a very deep time interval, whatever volume has to come in, that has to go out. Otherwise, it means there's accumulation of water at the junction. And junction is a point, cannot have volume. A similar way, the junction is a point. Can the point have net charge? No, it cannot have net charge. It's based on the fact that junction cannot have any net charge. There cannot be accumulation or depletion of charge at the junction. So if we apply conservation of charge, the charge coming in a time interval has to be equal to charge going out. So in case if it is not steady, I can apply over a time interval, or I can apply to instantaneous value of current also.
Yes.
And so at an instance, if there are 4 points, so instantaneous values of currents are there, I can apply to instantaneous values as well. Not necessarily steady. Okay.
Yes, sir.
Even it's varying, in that case, I have to integrate the currents which are coming in, total charge coming in from different branches equal to total charge going out from all branches over a time interval or instantaneous value. Either way I can apply.
Yes, sir.
Kirchhoff junction rule, loop rule, we have briefly discussed as we traverse a loop. Algebraic sum of all changes potential is 0. And we can start from any point in the circuit. Any point can be chosen as starting point. And loop can be traversed, or we can virtually move around the loop in any direction, clockwise or anti-clockwise sense. Only thing what has to happen, whichever point we started from, we should end up at the same point. The loop can be traversed either in clockwise or anti-clockwise sense to reach the starting point. Loop is very simple, and next month or so, we will apply this rule so many times, and it's good that you get used to it. So in this case, when you apply, since algebraic sum, again we have to define what is positive. So when the potential increases is taken as positive and drop is taken as negative. So there are two cases we come across. In case of battery, we may move from positive terminal to negative terminal, or we move from negative to positive. When we move from negative to positive terminal, it's an increase in potential, we'll take as positive. And similar way, when we move along the resistance, if the current is flowing, which direction? If the current is flowing from A to B, it means A has to have higher potential, B has to have lower potential. So in the direction of current, potential drops. So when is the potential rises? When we move opposite to direction of current. I'll give an example so that we understand this point. The law is very simple, methodical, and there's some sense also. If we move against the direction of current, in the direction as we flow along the direction of current is something like this. If we move in the direction of flow of the river, potential energy will always drop. The river flows on the basis of what is causing river to flow, loss of potential energy. Similarly, the current also is flowing in a particular, if it is flowing from A to B, is potential energy is dropping. Potential is dropping. In the direction of current flow, potential drops. Opposite to direction of current flow, potential rises. So that's why positive if we move against direction of current. So we'll take one example and we'll apply Kirchhoff loop rule in this example. So loop, it not be a closed loop. There are other branches as well. And it is part of a bigger circuit. Suppose this loop is given, I need to write an equation which involves application of Kirchhoff loop. First thing what I need to do, I need to choose a starting point and choose the direction in which I'll go about. So let me choose A as the starting point and let me go in the clockwise sense. So basically, I will virtually traverse the loop, or I'll virtually travel along the loop in clockwise sense, starting from A, ending with A. And what I'm going to do, as we traverse the loop, potential we see as we move from here to here, we assume there's no change in potential. But as we cross the resistance, there's a change in potential. And as we cross a battery, there's a change in potential. And later on, if also involves capacitor, when we cross a capacitor, it involves change in potential. And depending on which way are we moving, we write the sign plus and minus. So let's do it carefully. For this circuit, the starting point is A. We start from A and start in the clockwise sense. So first thing we'll cross is R1. Are we moving the direction of current or opposite to direction of current? As I move from left to right, I am moving in the direction of current, potential will drop. First thing, sign is negative. So let me write first, I'll come across potential difference across R1. Since direction of traversing the loop or my direction of virtual motion is along the direction of current, hence first I write the sign and then I1 R1. That's the potential drop. Then from here, the first thing I've done, then I continue moving from here, come to B. Then since I'm traveling the loop, turn the direction, come to R2. Again, I noticed what is the direction of current in R2. The current has changed. Why I1 and I2 are not equal? At this point, there's some branches. Some current may flow in here. So I can find out. So I2 is given, which is not necessarily same as I1. Had it been isolated loop, I1 would have been equal to I2. I hope that point is also understood. So again, we are traveling in the direction of current. So what should be the sign? First, every time let's mark the sign first. Since we are moving the direction, sign is negative, minus I2 R2. Then from here, we come to point C. And then from here, we come up to this point. So from here to here, no change in potential. Now I'm crossing the battery. I'm going from negative to positive. Should the sign be plus or minus? We are defined potential increasing or decreasing. As we go from negative to positive, potential is increasing. Hence, the sign should be positive. I put as plus E1. Then again cross R3. R3 again in the direction of current. Hence, again the minus sign, minus R3R, minus I3R3. But when I come here, what I find now, I'm going, which direction I'm going? Upwards. Which direction current flowing? Downwards. So here now the direction in which we traverse resistance R4 is opposite to direction of current. Hence, this one will come as positive. I hope this point is well understood. Plus I4 R4. Then again, I cross the battery from positive to negative. Positive to negative is minus E2. And I reach back the same point A. So I equate it to 0. Thus, application of Kirchhoff loop rule. Only thing which is of matter is sign. And there are two very simple rules. If we are moving along the direction of current, negative, opposite direction of current, positive. In case of battery, from negative to positive terminal is positive. From positive to negative is negative sign. So I hope all of you find this simple enough. Please make sure it is well understood. And as we go along, we'll apply multiple times. And it's better you get accuracy right in the beginning. So this is simple application of Kirchhoff loop rule. So two laws, junction law and loop law. Both are fairly simple. Now we have started from point A. Somebody say I could have started from somewhere else? What will happen if we choose a different starting point? Suppose I started from B. What would have happened? The first term would have been this term. Next term will this one, this one, this one. Only thing what happened had we started from B, this term minus I1 R1, which is coming in the beginning, its order would have become last. So if I go in the same direction, if I choose any other different starting point, only the order of terms in this equation will change, equation will not change. So whichever point, if you start from C and go in this direction, E would have been the first term, this term would have come last. So it doesn't matter which point you start with. Yes, Ashray?
Sir, I wanted to know what exactly does a resistor do, sir?
What is a resistor?
What is a resistor used for?
Resistor used for? Huh?
Yes, sir.
Okay. See, any electrical circuit is like a loop. So when you have a circuit, there are different circuit elements. Now your question may come, why do we use electrical circuit? All electronic devices are composed of flow of charge. Even human body also, I think you might know, some of you might be aware of, every time you move a muscle, the brain has to send a signal to the muscle to move. How the signal is sent? Signal is sent in form of a small current. It is order of microampere. So any circuit has current flow. When the charge flows, charge flow leads to current. And whenever current flows through any device, if it is a wire, it will have resistance. It is impossible to have zero resistance. Resistance may be small, but it still has zero resistance. So when the resistance when it moves across the resistance, we'll see later, as it moves across resistance, the word resistance indicate it offers resistance to flow of charge. Why does it offer resistance to flow of charge? Flow of charges, electrons start getting accelerated. The collision leads to loss of energy, that's the resistance. So resistance is invariably will be there. So why we need to resistance? Sometimes we don't want resistance, but it is there. And we need to account for its effect. Its effect is in terms of loss of energy. Effect could be in terms of change in potential drops. So we first will understand what is the effect of resistance on current, how the charge will flow, how the current will flow. Yes, resistance affects that. So suppose you connect a battery, how much current will flow? It depends on resistance. So knowledge of resistance is important. Once we have the knowledge of something, then we can apply it for different purposes. So I hope you understand this important point here. See, many things, there's something called Faraday law. When he invented Faraday law, somebody asked him, what is the use of this law? You invented a law. Is this law of practical significance? His reply was, this is a new knowledge. It's like the new child which is born. What the child will do later on, we don't know. So once we have knowledge, then people start thinking, this knowledge, how do I put to use? So resistance is something we understand. Okay, so to make the charge flow across any conductor, we need to apply potential difference. And when you apply potential difference for different type of material, the current is different. The current is different, so the ratio V and I is different. We have defined the VI by ratio as resistance. So resistance is a name what we use to define certain relationship between physical properties. And what is the use of the resistance? We'll see later. One of the use of resistance could be sometimes it is useful. Where the resistance is useful, sometimes we want resistance, we want dissipation of energy. Your geyser, what we use at home, is example of that. How does geyser work? We make the current flow through the resistance. Resistance is like a coil. It gets
Heating
heated
effect.
up and it heats the water. But sometimes it's useful, sometimes not desirable. But we need to know how it functions, what current it will allow, what potential drop will take place. So always understand, see, many times when the students also think, what is the use of learning maths? To understand use of maths, unless you learn adequately, then only start seeing where it is put to use. Every damn thing, whatever progress science has made, it has made because of knowledge. So first you acquire knowledge and then you see how to use it. Some people go in the reverse order. First you tell me how do I use it, then I will think of acquiring knowledge. Your knowledge is so low, you can't even understand how it can be put to use. So that's beside the point, but I hope you understood what I said, some of you. Does it make some sense? Asha, you understood something or no?
Yes, sir.
Okay. So resistance in every device is not only in this topic, every topic we understand the behavior. See, science is the study of nature, how things behave. And once we understand how it behaves, we can predict what will happen and we can plan also something to happen. Okay, so resistance also is something. What resistance? So whenever we try to create a charge flow across any conductor, it could be insulator also, we see later. It could be even semiconductor. But initially start our understanding with simpler thing, which is resistance. Whenever we try to make a current to flow, we need to apply potential difference. There has to be energy level difference between the two ends. Okay. And when you apply potential difference, different cases, different current will flow. So there's a particular ratio. In many cases, the ratio is constant, which is Ohm's law. And what is the resistance? Resistance is nothing but ratio of V by I. Okay. So let's proceed further from here. I hope all of you understood Kirchhoff loop rule and you have understood something about what he said about resistance and why understanding not only resistance of so many things is vital, important. And once we know the knowledge, once we have the knowledge, we can put to a variety of these. And this is actually pretty simple derivation, but let's go through resistance combination we have done in case of capacitor. Something similar happens in case of resistance. So what if potential difference is something? So what is resistance? As we mentioned, we already said, what is resistance? The ratio between V and I. Okay. So if 2 points are there, A and B, if we apply potential difference V between 2 points, and if the current is I know the resistance is V by I. It could be because of one resistor, it could be because of combination of resistors. So what is the resistance between 2 points? Resistance between 2 points depends on ratio of potential applied to those 2 points and the current will flow from the starting point. That's the resistance. That's the side. What is the combination? Potential difference we apply to 2 points of a combination of resistors. If the combination draws a current I. So how do we find if we have all kind of network, it's a complex network of resistors you are there. If I have to find resistance between 2 points, if I've known potential, if I apply and check what current flows, that is enough to find the equivalent resistance of the combination. What is R equivalent? That R equivalent is V by I. It could be one single resistance. So if I want to replace in one single resistor, yes, entire combination can be replaced with one single resistance Req. Its behavior in terms of resistance will be the same. Other behaviors might change, its capacitor behavior, but resistance, as far as resistance goes, a combination of resistance can be replaced by one single resistance called Req, which draws same current when same voltage is applied. That's the logic behind it for finding combination. So resistance Req. So rather than having this combination, if I have this Req with one single resistance, for same voltage, if you draw the same current, this Req is equivalent of this combination. That's what these two statements mean. Let's apply series combination. So let's we have defined series combination in case of capacitors. How did we define series combination in case of capacitor? Direct connection. No, so that the charge, if one has charge minus Q, other will charge have plus Q. net charge remains 0. There's no diversion of the charge. Charge remains, there's no branch in between. Series combination also is similar. Resistors are connected with considered to connected in series if same current passes through all of them. There the charge was same, here the current is same. So when connected, how would the same current pass through? So here we see R1, R2, R3. When we look at this, intuitively we feel that they are connected in series. But what is the proof that they are in series? Whatever current passes through R1 must pass through. So how the current will be same? Whatever current passing through R1. If the junction between R1 and R2 does not have any branch, so if there's no branch, it means there's no scope for any current to leave in between, any current to join in between. If there's no current joining or leaving in between, what does it mean? The current in R1 and R2 are same. So connection between two resistors, if do not have any branch for either any current to leave or join in, then it's called a series connection. Both are similar thing. I hope this is easily understood. So if it's series connection, whatever current passes through R1, same current passes through all resistors. So when you connected this battery, at this junction, if current is I1, same current will pass through R1. What is the current through? Same R1. If I is the current through R1, same current I will pass through R2 if it's series connection. And we answer logic also simple. This junction, if we take whatever current has come in, same current has to go out. Junction rule also. And here also, the junction is only junction also has only two elements: current coming in and current going out. Both have to be equal. So this is series combination. Same current flows through all. In case of capacitor, same charge on all capacitors connected in series. Okay. And so when we replace with equivalent resistance also, so we can say whatever current flows through equivalent resistance, same current will flow through all resistances connected in series combination. Okay. So let's find its value. How do we find equivalent value? Let's proceed with this. So first case, what the current is, I can apply Kirchhoff loop rule starting from A. If I write Kirchhoff loop rule, now I'm not writing so much detail. All cases as we move from A to B, everywhere I am moving in along the direction of current. So all I into R1, I into R2, I into R3, all terms will be negative. So I apply Kirchhoff loop rule starting from A going in clockwise direction. First term minus I into R1, second term minus I into R2, third term minus I into R. Sorry, this is I might be bad, but there's something. It's all I1, R2, all are R1, R2, R3. This is R2, and third one is R3. Okay. So these are the and then what? So this is resistance part. What is left? Okay. So I1, R2, R3. And then after B, we move like this. Then we cross this battery. We go from negative to positive terminal, hence plus. Okay, this is the equation we get applying Kirchhoff loop rule. And okay. And what is R equivalent? R equivalent is V by I. Can we find out ratio V by I from here? If I find V by I ratio is equal to R1 plus R2 plus R3. So which gives you R equivalent is equal to R1 plus R2 plus R3, which is very, we have known that one. So in case of series combination, equivalent resistance is sum of the individual resistance. Now let's understand what is the potential difference across each resistance. Let me take all V1. What is V1 here? V1 is the potential difference across resistor R1. So I can write V1 also is equal to VA minus VC. Potential difference at its terminals. What is the magnitude of potential difference? That is magnitude of potential difference equal to I into R1. So potential drop across first resistance. Potential drop when we talk about potential drop across the first resistor, which is VA minus VC, is equal to I into R1. Similarly, if I write V2, what would V2 signify? V2 signifies potential drop across second resistor R2, and V2 will be equal to VC minus VD. Okay, V2 will be equal to Vc minus Vd. What is Vc minus Vd will be equal to I into R2. And similar way, V3 indicates here potential drop across third resistance, which is Vd minus Vb, which is equal to IR3. So what I notice here, the potential drop across three resistors are in proportion of the resistance. All are proportional to resistance. The potential drop is shared. So total V, if potential V is applied across a combination of resistors connected in series, it will be shared among all the resistors which are connected in series. Which proportion it will be shared in? It will be shared in proportion of their resistance. So one which has highest resistance will have higher potential drop. Or other way of saying, since the current is same, to push same current through the different resistor, I need higher potential drop to push same current through higher resistance. Okay, so potential drop is shared in proportion of resistance. And we should know how to quickly calculate potential drop across each resistance. We'll practice some more questions on this. Then we look at, that was very simple. So what happens in case of parallel series now we come to parallel combination also. Parallel combination, how did we define parallel combination in case of capacitor? The capacitor has two plates, two terminals. If the terminals are connected to identical potential points, they were supposed to be in parallel. Similar to capacitor, even the resistor also has two terminals. And for that matter, most circuit elements will have two terminals, two ends, and they are connected to two ends in a circuit. So resistors are said to be connected in parallel if they are connected across identical potential points. So this definition and understanding is identical to what we had in case of capacitor. So if you understood how to identify parallel capacitor, similar logic can be applied to identify resistors connected in parallel. Definition is exactly the same, very similar way you can do. Only thing what happens here, so in this case, equivalent. So if this combination of resistors are connected across potential V, current goes I. So if you have equivalent resistance also, when you connect, the current should be I. But as the current I goes here, there's a junction here. Each part, this one has I1, this has I2, and this is I3. So we can easily, based on applying Kirchhoff junction rule here, we can easily arrive at this equation, I is equal to I1 plus I2 plus I3. So we'll find out equivalent resistance by substituting the value of I1, I2, I3 in this equation. Okay, calculation of I is simple. Calculation of I calculate from this circuit. Calculation I is equal to V by Req. Similar way, I'll calculate I1. What is I1 here? Current is equal to potential drop divided by the resistance. So for what is the potential drop? VA minus VB, which is V. I1 is equal to V by R1. Similarly, I2 is equal to V by R2. And I3 will equal to V by R3. So if I substitute this value of I and I1, I2, I3, V term will cancel out and we get the expression for equivalent resistance. 1 by Req is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is something which I had known. And other thing what we noticed here, in case of series combination, current is common, potential is shared in proportion of resistance. Here potential is common, current is shared. So if current I is coming into a combination of parallel resistors, it will be split or shared in which proportion? In inverse proportion of resistance. So current is shared in inverse proportion of resistance, or the current follows the path of least resistance. More current will flow along the path which offers lower resistance. Okay, so this is parallel combination, nothing very surprising, nothing very new. What happens in case of parallel combination, as we had in case of capacitance also in inverse combination? The equivalent resistance is always less than the least of the three resistances. Equivalent resistance is always less than the least of the three resistances. If I connect resistance of 1, 2, and 3, even before I find the value, I know the equivalent resistance will be less than 1. So anything when we add something in parallel, it always reduces the resistance between the 2 points across which it is connected. So take one, so what happens if one of the resistors connected in parallel has 0 resistance? Suppose I say here, if R1 is 0, what is the equivalent resistance between A and B? If you put R1 is equal to 0, what happens? This whole term becomes infinity, or R equivalent becomes 0. So whenever number of resistances are connected in parallel, if one of the resistance is 0, or we are saying if the resistances are shorted, the equivalent resistance drops to 0. What will happen in this case? If the current flows like this, will there be any I2 and I3? Entire current will flow through the path of 0 resistance. So if R1 is 0, I1 will be equal to I, and I2 and I3 will be equal to 0. No current will flow through path having resistance if one path is available which offer 0 resistance. So far, any issue, any doubt, any query, any statement? These are very basic stuff, and most of it you have done it in junior classes also. You know what is equivalent resistance. In case of parallel and series, only thing we'll do in much more detail, and hopefully with better understanding and better clarity. Okay, so let's look at some of the application. We have understood this part. 2 important points only. In case of series combination, how to identify series combination, which is not tough. Current is common, potential gets shared in proportional resistance. In case of parallel combination, is not first part, how to identify resistors connected in parallel, identical potential points, and then potential is common, current is shared. Which proportion it is shared? Inverse proportion of resistance. Okay, and I think we know enough simple mathematics to divide current in inverse proportion without trying to convert into kind of formula. I don't think it's any need to write a formula for inverse proportion, but some of you feel necessary, you can do so also. Let's do some simple questions, and what I expect, they're extremely simple questions. One I'll explain, rest of question I expect all of you to solve. So I would ask some of you, you should respond and answer. This question, this is a circuit given, what we need to do, assuming that potential at the negative terminal of a battery is 0. Find potential at point A, C, and B, and also find the current. Because to find potential, maybe current also required. So find current and find the potential at 3 different points. Approach to this question is similar to what we had done in case of capacitor. Let's do that part. One way of solving this question is, first I find out current, then I know the potential difference between 2 points across the resistance will be I into resistance, current into resistance, and I can use that method. Equivalent resistance, there are 2 are in series. Equivalent resistance is 15 ohms between across the battery terminals. If equivalent resistance is 15 ohms, I can find current. Current is equal to V by R. So the current flowing is equal to 12 by 15, which is 0.8 amperes. So 0.8 of amperes current flows. So we apply Ohm's law across 10 ohm resistance. So I know the current here. Current is 0.8 amperes. If current is known, I can find out potential using Ohm's law. V is equal to IR. So what is potential difference? What is, when we talk about, when you apply Ohm's law for a resistor, what does V indicate? V indicates potential difference across the endpoints of the resistance, and I indicates current flowing it. And when we take potential difference, we take from which point to which point. If the current is flowing in from C to D, potential also we take VC minus VD. So when we apply, this is something I'm applying Kirchhoff's law, sorry, Ohm's law. So VC minus VD, I'm applying across 10 ohm resistance. VC minus VD is equal to current into resistance, 0.8 into 10. 0.8 is amperes current, 10 is the resistance. That comes to equal to 8 volts. We know the potential of B is same as potential of negative terminal. BB is 0. So, sorry, I think VC not VC. It should be this time. VC it should be VC minus VB. So this gives you value of VC minus VB is 8 volts. Since VB is 0, VC becomes equal to 8 volts. So I have found the potential at this point. What is potential of A? Actually, I don't have to calculate. Potential of A is same as the potential of the positive plate. If negative plate is 0, this will be 12 volts. Or I can calculate that also using applying Kirchhoff, using applying Ohm's law. So this becomes 0 volt. This becomes 8 volts. And then I can apply VA minus VC. Potential difference across this resistance equal to I into R. So 0.8 into 5. This is equal to 4 volts. VC is equal to 8 volts. If I substitute VC is equal to 8 volts, VA comes equal to 12 volts. So these are voltages. 0 volts, 8 volts, 12 volts. It means between 2 points, what is the potential drop? Potential drop here is 4 volts. What is potential drop here? 8 volts. Does it make sense this potential drop is 4 volts and this is 8 volts? Yes. Because to push same current, I need higher potential difference across higher resistance. So you have understood potential drop difference across 5 ohms is this minus this, which is 4, and this minus this is 8. So very simple question, very basic question, but basic question also we should be handling. So we could have done in terms of division of voltage. What I could have done, total potential drop is 12 volts. It will get divided into two parts, V1 and V2. What is V1 and V2? It will be shared in proportion of the resistance. So this will be the share of 1:2. One portion here, two portion here. So what will the V1 in that case? If we divide into ratio 1:2, it becomes 4 and 8. So V1 will be equal to 4 volts and V2 will equal to 8 volts. V1 and V2 indicates potential drop. So I could have done in terms of, either I could have done in terms of calculation of current and then calculating potential drop is equal to I into R. Second, I could have done directly in terms of division of voltage in case of series resistance. Division of voltage or distribution of voltage is in proportion of resistance. Very simple point I'm repeating again so they're absolutely perfect in this. Suppose circuit is given like this, not 5 volts or not 10 volts. It is given as 2 ohms, sorry, 2 or not 5 and 10 ohms. It is 2 ohms and 4 ohms. Is the potential at point A, C, B same or different?
Same.
Same.
Same,
Same
sir.
ratio.
Potential difference will come. So potential will come same. So as long as the ratios are same, potential differences will be same. And since potential difference is same, potential also will come same. Only thing what will happen, this current will change. Okay. So can you all calculate potential for this point A, C, B? Please calculate potential at point A, C, B, assuming negative terminal to be 0. Actually, A and B are easy. B will become 0, A will become 6. Only thing what you need to calculate is potential at C. So all of you, I expect all of you to have an answer. All of you try and get an answer. And any person I ask should respond and give an answer. You cannot be just sitting, this answer, this questions, everybody should be able to solve if you have paid slightest of attention. So I'll give 2 minutes. After 2 minutes, when I ask question, I expect answer from everyone. Before I ask another question. Please respond now. Listen carefully, all of you. Those who are not able to speak, either because they are not connected to microphone or they are not connected, they don't know how to unmute. Please raise your hand now. So I know who are the people who cannot respond. So you show your hands now. Afterwards, if I ask question, if you do not respond, you are out of the class. So those who cannot answer for whatever reason, and I respect your reason. So I'm not questioning those who have problem speaking for whatever reason. Please raise your hand so I know who are the people who cannot respond. Rest of the people, okay. So rest people, I expect answer. Samita, Neha. Okay, so other than this, rest of the people should respond. Okay. Suddenly it's waking up so late, Sweta. Why it took so much of time to respond? At least raising your hand should be done quickly. Tejas, why you're so slow? Tejas, you okay?
Forgot to raise my hand, sir.
Who? That is, you are not listening. Who are supposed to raise hand? Those who cannot respond. Those who have audio not connected, either they cannot unmute themselves or they don't have a mic. Only those people.
Oh, sorry, sir.
Sorry, that's why I'm surprised. Okay. The rest of the people, if you don't respond, okay. Rest of the people, I expect you to respond. Now coming back to this question. This is extremely easy question. I want an answer in terms of what is potential at C. Rest of people don't answer. I ask some people, only those students I ask should answer. And answer should be quick. Answer should be in terms of what is the potential at C. And this is extremely simple. Just now we have calculated, and you should know how to do it. Okay. Anirudh,
Yes, sir.
what is potential at point C? Can you calculate and tell me the answer?
Sir, it's 3.6 volts.
3.6 volts. Good. That's what I expected. Very nice. So at least simple questions as I ask, you should answer. Is it difficult to calculate? Both ways you can calculate. Again, I'll go through. First, I'm happy that first person I asked has answered. So one way of calculation would be, I can calculate equivalent resistance. Again, I'll repeat the process. Equivalent resistance between A and B, which is 10 ohms. Then I calculate current, which is 0.6 amperes. I can apply Ohm's law across each of the resistance. When I apply across these two, Ohm's law, VC minus VB, again, I think the typing D, my mistake has come. So current interval, this is 3.6 volts, which gives you voltage at C is equal to 3.6. So these are the voltages. And what does this mean? Potential difference across A and C is 2.4. Potential difference across C and B is equal to 3.6. I could have done in terms of division of voltage also. Division of voltage, I could use this formula. Division of voltage is this one. R1 divided by summation of all resistances into B. Okay, this is pretty simple. So I'll do some more. Again, next question. Again, I expect all of you to find an answer, and only those I ask should answer. This answer should be in terms of V. Calculate potential at C. We know VB is 0, VA is equal to V. What is potential at C? All of you should calculate. I'll give you half a minute, but when I answer after a minute, ask, all of you should answer. Srishant? 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 Gautami? Gautami? Srishant, can you hear me?
Sir?
Okay. Srishant. Gautami, remove Srishant. Let him
Okay,
go out
sir.
of the class. Okay, he is not responding. Srishant, he has not given his name. So when I rotate this name down, his name was not there. Not listening. No need to be in the class, and I'll talk to him again after the class. Pranav Soma.
Yes, sir.
Do you have an answer? What is the potential at point C?
2V by 5, sir.
Huh?
2V by
2V by 5. Any problem in finding potential? Yeah, perfectly okay.
okay, sir.
So both ways you can calculate. One way you can calculate through current, another we can calculate for product. And that's why I said this question I expect everybody should be able to solve. So you're able to solve. Next question. Again, I give a minute of time. All of you should solve, and whosoever I ask should respond. And hopefully with the correct answer. Okay, I think he had enough time. Joshua. Joshua. Joshua.
Joshua
Yes.
actually raised his hand.
Achha, he raised his hand.
Yeah.
Yes.
Oh, I think in the name I missed the writing. Okay, good. He raised his hand. Okay. Akshay. Akshay also raised his hand. Sorry. So let me ask who was the person. Okay. Shachi.
Yes, sir.
Okay, today your mic is working. Can you tell me what is the potential at point C?
5V by 6.
Yes, correct. Are these difficult questions? No. But they are very basic for solving all questions involving current electricity. If you people get it so perfect you can do in mind, it helps rest of the task becomes extremely simple. That's why I'm repeating this point. They're extremely simple. What is the logic I can think of? Since potential at B is 0, V2 is equal to potential at C. And what is V2 equal to? Very simple. 5V by 6. Okay. Similarly, find potential across resistances connected. Now this time I have to find VC as well as VD. Can we easily find VC as well as VD? Earlier there were only 2 resistances connected. Now there are 3 of them. Should it be difficult to find VC and VD? It should not be. So again, I give about a minute of time. All of you have your answer ready in your mind. So whosoever I ask should answer. Shreya, do you have an answer?
Yes.
Tell me what is VC and what is VD. Assuming that VB is equal to 0. All the time we are assuming that negative terminal battery is 0. So what is VC and what can you tell me?
VD will be V by 3, sir.
Yes.
So
And VC?
VC minus V by 3 will be the potential across the middle resistance.
Okay. So what is VC value will come to? See, one way of thinking would be, another way of thinking what? See, their resistances are equal. If I apply voltage of V, potential drop across each one of them is V by 3. So from here it is 0, this is 0 plus V by 3. What is VC? Again plus V by 3, 2V by 3. And V, 2V by 3, V by 3 and 0. So this kind of thing you should be able to do very quickly in the mind, no problem at all. Potential drop, V by 3, V by 3, V by 3, and then we can mark the potential. Similar way, now this time, all of you calculate for this circuit. What is VC and what is VD? And we written potential drop can be written in, yes, it is in proportion of. So this time I am not asking potential at point C and D, I am asking potential difference across resistance. So what is potential difference across this one? What is V1? What is V2 and what is V3? Please calculate this kind of number. What is V1, what is V2, what is V3? And we should have an answer very quickly. Akul,
Yes.
Can you tell me? Yes.
So the potential drop will be 2V by 7.
Why 7? Where from you getting 7?
Oh, wait, no. I calculated wrong. Sorry.
Okay. Correct that one. So how much that would be? So if between A and C, how much will you?
V by 3.
Yes. V by 3.
Sorry.
Right one. Okay. This one V by 3. Okay.
Then 2V by 3.
So any problem you have, Akul? Are you clear about this part? Absolutely
Yes.
no problem.
No, sir.
And
I am.
see, V by 6, V by 3, and V by 2. Okay. So where you can also think of this. If you divide in proportion of resistance across this, sum of the 3 is 6. So R by 6R into V, 2R by 6R into V, 3R by 6R into V. Extremely simple. That's why I said if somebody is not answering this question, it means you are not paying any attention at all. So they are simple question. Now I come to the second part. So first case, what you have done, in case of resistors connected in series, I should be able to find very quickly potential at different points and potential difference across resistances. Now in case of parallel combination, if assuming that current I is coming into the junction, I should quickly figure out how the current will get distributed. How much will be I1, how much will be I2. This also I should be perfect, so that I am perfect and quick, so that I can quickly do in my mind how the current gets distributed. Here the current gets distributed in inverse proportion of resistance. So what is this happening? If I apply junction rule, if I current is coming in, going out is I1 plus I2. So by junction rule, I is equal to I1 plus I2. And since they are identical potential, I1 into R or I1 into R1 has to be equal to I2 into R2. In this case, I1 into R has to be equal to I2 into 3R. So either I can do that or I can do inverse proportion. So what is inverse proportion if R and 3R? Which will have more current flowing in? Of course, the one which has lesser resistance will have more current flowing in. How many times more? Since resistance is what 1/3, current will be 3 times more than I2. I will be 3 times more. Or I'm saying dividing the current in inverse proportion of resistance. Can we easily do that part? Applying I1, R1, R2. I can write I1 as, what is I1? If it is inverse proportion, in numerator what comes? R2 part. R2 divided by R1 plus R2 into I. Or I can do it mentally also very quickly. So how much for 3/4 of current will flow here? 1/4 of the current will go here. So 3/4, it becomes 3 times of that. So finding whichever method you want to use, you can use formula, you can do like formula like this. But I think it's much better if you understand to divide in inverse proportional resistance in mind. So that is much better rather than everything converting to formula, doing in how we solve in class 6, 7, 8. Okay, so this is something 3/4I and I/4. So what I expect next time, again, whatever questions appear on the board by screen, all of you should be able to divide the current quickly. If this is the current, can we find I1 and I2? So what I expect now, all of you calculate in your mind how much is I1, how much is I2. Have that answer ready. So when I ask you, you should give me I1 first, I2 next. Vrinda, do you have an answer? So Vrinda did not raise her hand. Huh? Some of you I don't see. Vrinda, are you connected to audio? As per my screen, I don't connect you, but I think you didn't raise your hand as well. Or maybe, no, I didn't see. Okay, let's ask someone else then. Ved Vyas. Ved Vyas, did he raise his hand? Ved Vyas?
Yes, sir.
I didn't. Why?
No, sir. It's me. I'm responding.
Okay. So can you tell me I1 and I2, Ved Vyas?
No, sir.
Why not? Formula is there on the screen. Just to explain, inverse proportional resistance, still you're not able to do it. If I have to calculate I1, what is R2 here? If I calculate this one is I1, which one is R2? What is the value of R2 here, Ved Vyas?
12 ohms.
12 ohms. And what? So and what is I1? So what is in the denominator? 12 divided by 12 plus 5 into I. I is 10. So simple formula also. How can you not substitute that also? What is I1 equal to 12 divided by
17.
17 into 10. What is difficult in that? And you should practice that one, and you should be able to do that. As there's no reason, no excuse at all why you should not be able to do something as simple. Okay. I think those questions you left with. So I'll stop here, and since your next test is on capacitor, so evening session, if you're interested, I'll take up some more question based on this and give some simple question for assignment. Okay. So let the session here. Yes. Anybody has any question?
Sir, I have a doubt, sir.
Yes, please. So those who do not have any doubt on something, they can sign off. Anybody, any doubt, can you just stay back? Okay. What doubt you have?
Sir, in the loop rule, when we go in the direction of the current, we assume that there's always a potential drop, right? So because the direction of the flow of charge is in the direction of potential drop.
Without potential drop, the current cannot take. See, when we say V is equal to IR, what does V mean?
the potential difference across the ends of the.
So can there be can the current flow without potential difference?
No, sir.
No. So there cannot be any current flow without potential difference. That is one part you understood. And if current is flowing from A to B, can potential of B be higher?
No, sir. Potential of A should be higher.
No, that's what I'm saying. So if the current is flowing A to B, it definitely indicates potential A is higher. So if I move from A to B, what will happen? Potential will drop.
Yes, sir. Thank you, sir.
Yeah, good. Not only law, we should understand what is it, does it make sense? Does it make logical sense? I think yes, it does make logical sense. And it's not
Yes,
too difficult to comprehend also. Okay. Anybody else has any other question?